Thank you very much for the invitation. I'm very happy to be virtually there and to tell you about something that I've been very interested in the past few years, which is the connection between strings on AdS3, Tsd transformations, and irrelevant deformations of 2D CFTs. So in the past few years, we have learned that there's a special class of irrelevant deformations that have some remarkable properties. And these are irrelevant deformations that are made up of the antisymmetric product of two conserved currents. So they're written down here. And I have written these currents as one form so that the wedge takes care of the antisymmetrization. These deformations are universal and do not depend on the details of the QFT. Of course, this QFT must have symmetries for which you can write down these currents. They preserve integrability of the underlying QFT, if there's any to start with, and provide examples of non-local but UV-complete QFTs with a novel UV behavior. And I will mention something about the UV completeness on the next slide. So the simplest examples of these deformations are the so-called TTbar and JTbar deformations. For TTbar, we can write this current in the following way. And the deformation parameter has dimensions of length square, so this is an irrelevant deformation. Similarly, for JTbar, we can write this current in terms of a U1 current, J here, and similarly this one. And the deformation parameter has dimensions of length. It's also an irrelevant deformation. These deformations are solvable in the sense that we can derive the spectrum and this matrix of the deformed theories in terms of the undeformed quantities. So for example, for TTbar, I have written down the energy. Here is 0 and J0 are the undeformed quantities. And this square root structure is characteristic of this type of deformations. You also find it for the JTbar deformation, for example. And similarly, you can write the deformist matrix in terms of the undeformed one, and you only get an additional phase factor. And something similar happens for the JTbar deformation. Interestingly, it is, yeah?
What is Pi and Pj in the exponent?
Pi and Pj are the momenta. So here, these are the momenta of the incoming and outgoing particles. So for example, for JTbar, one of these P's will be changed by a Q, one of the charges of the particle, of the incoming or outgoing particle. Mm-hmm. Yeah, and so, so please feel free to interrupt me if you have any questions. So the deformed theories share many features with theories of 2D quantum gravity, including a minimum length scale, non-locality, and universal time delay in scattering. And interestingly, all of these properties can be deduced just from this deformist matrix. And the fact that this S matrix is defined all the way to arbitrarily high energy, so all the way to the UV, is what tells us that these deformations are well defined there. Now, a natural question to ask is, what is the holographic dual of such a deformed CFT? So you can imagine that I start in the IR with some two-dimensional CFT that meets all of the conditions to be holographically dual to Einstein gravity in AdS3. On the left-hand side, you turn on the deformation by TTbar, JTbar, or some linear combination of them. And then you ask, what is the deformed theory of gravity? Now, it turns out that to answer this question, we need to distinguish between the double and single trace versions of the deformation. So to distinguish them, let me consider string theory on AdS3 times some internal manifold, which for concreteness, I'm taking to be S3 times T4, with only NS and S flux, so that we only have a metric, a P field, and a dilaton. Why do we have only NS and S flux? Because in this case, we have a perturbative worldsheet description in terms of an SL2 Witten model, and this will be useful when we try to get evidence for connections to TTbar and JTbar. Now, there are two representations of SL2 that play an important role in string theory. There are the discrete or short string representations and the continuous or long string representations. And we will see later on why are they called this way. And in the last few years, there has been a lot of development in trying to understand what the holographic dual of this theory is a string theory in AdS3 with pure NS and S flux. And the lesson that we've learned is that the long string sector of string theory seems to be dual to a symmetric orbifold. Okay, so here I've written down the symmetric orbifold. This M is the seed theory, which for the background that I showed you before is conjectured to be Liouville with central charge 6k-1 times the sigma model on T4, so that the central charge of the seed theory, this M, is 6k, and the full central charge of the symmetric orbifold is just 6kp. In this talk, so P is related to the string coupling in the following way, and we're going to take this to be large to have a weakly coupled worldsheet description, and K is related, this doesn't look like K. K is related to the ratio of the AdS scale to the string scale, and it's also taken to be much greater than 1, so that we have a nice semi-classical description in terms of supergravity. Now, why am I introducing the symmetric orbifold? Is because the structure of the symmetric orbifold allows us to define two kinds of deformations. So there's the double trace deformation, which I've written here, where you deform the full theory. So the full theory by this antisymmetric product of conserved currents. Here, this J can be written as a sum over the currents on each copy of the symmetric orbifold, so that I can also write it in this way on the right-hand side, where you see that there's a sum, that there are two sums. But alternatively, because of the structure of the symmetric product, I can define a single trace version of the deformation, where I take each of the theories and I deform it by the corresponding antisymmetric product of conserved currents, and so on. So in this case, a single trace deformation is defined this way, and you see that the difference is that there's only one sum. It's single trace. Now, what's interesting about this single trace deformation is that it takes a symmetric orbifold and gives you another symmetric orbifold. So all that we accomplished by the single trace deformation is that we've changed the seed theory, so that each theory here in the copies of the symmetric orbifold now will be either a TTbar or a JTbar deform theory, or a linear combination of them. Surprisingly, the different versions of this deformation lead to different versions of holography. So the double trace version is conjectured to be dual to gravity in AdS3, where you put a cutoff, or gravity with modified boundary conditions. And in particular, in this version, you don't change the local bulk geometry. So you would still have AdS3 with some modified boundary conditions. But the single trace version does change the bulk geometry. And it's conjectured to be dual to the long string sector of string theory on either a linear dilaton background for the case of TTbar, or a warped AdS background for the case of JTbar. So what's interesting about this single trace deformation is that you're changing the background in the bulk, you're also changing the theory at the boundary. So we can interpret these cases as toy models of holography for non-AdS spacetimes. Okay, and for this reason in this talk, I will consider only the single trace version of holography. Okay, so more concretely in this talk, I will describe a systematic approach to generate backgrounds that are dual to states in single trace deformed CFTs. I will construct the most general class of black hole solutions in the space of these theories here by TTbar plus JTbar plus TJbar. I mean a linear combination of these deformations. And I will provide further evidence for the correspondence. So the outline of the talk will be as follows. I've already given you some motivation to study these deformations. Next, I will review how TTbar and JTbar first emerged in string theory. And I will use this review to motivate the connection between TsT transformations and irrelevant deformations. Then I will construct some TsT-transformed backgrounds and tell you some properties of these backgrounds. And by looking at these backgrounds, we will get many hints that these backgrounds have something to do with TTbar and JTbar. And then I will provide two evidences for the correspondence. There's a perturbative one, which will be the spectrum derived from the worldsheet, and there will be a non-perturbative one, which will come from studying the thermodynamics of what we call TsT black holes. Okay. Okay, so let me first review how TTbar and JTbar first appeared from the point of view of string theory. As before, we're taking string theory in this background, only with NSNS flux, and I'm only considering the bosonic sector. And in addition, for the AdS3 part of the background, I'm going to take the massless BTC black hole, which is locally the same as Boca AdS3. It just differs by a global identification on the coordinates. Why am I taking this background? Because a long time ago, Kutuzov and Seiberg were able to construct vertex operators that corresponds to currents in the dual CFT. These are the so-called DFF operators. So for example, they were able to construct the stress tensor in the dual CFT. Here, X is a coordinate in the dual CFT. It looks something like this. There's some bulk to boundary propagator that we don't need to concern ourselves too much with. And there's these so-called soldering currents that have coordinates in both the dual CFT and on the worldsheet. And this current depends on these other currents of the worldsheet, which are the currents that belong to SL2R. So string theory in this background can be described as a Wessel-Witten model, and one of the symmetries is a left-moving copy of SL2R. And similarly, you can define a UN current that is given here. And the ingredients that make up this current are, again, this bulk-to-boundary propagator, this soldering current, and an additional worldsheet current, which is, in this case, a current from the U1 factor of T4. Of course, you could have taken any other currents from either the S3 or T4, and something similar happens. Now, in this paper, Kutuzov and Seiberg found another set of vertex operators that mixes elements of T, T-bar, and J. So these were called the D and A operators. You see that these operators are no longer chiral. They depend on the both coordinates of the CFT. And they mix elements of T and T-bar and J. For example, this comes from T, this comes from T-bar. And you again have this bulk boundary propagator. And similarly for A, you have an element that comes from the J current above and one that comes from T-bar. So these are strong hints that these operators have something to do with TTbar and JTbar. And indeed, you can go ahead and compute the OPs between all of these currents. And you find that the Z operator, for example, has conformal dimension 2,2 on the dual CFT, meaning that it has the same quantum numbers as the TTbar deformation. And indeed, you can go ahead and compute the OPs, and you see that they look pretty similar. As they should, except that they differ on the most divergent term. So you see that the OP between T and TTbar has this additional factor of P. Now, in the context of holography, this P was counting the number of copies of the symmetric orbital. So this may have something to do with the structure of the symmetric orbital. And that's indeed the case. So what you can do is you can take the symmetric orbital here, and note that I don't need to specify what the seed theory is. You just take any symmetric orbital, and you compute the OP of the stress tensor with the single trace version of the TTbar operator. And the OP that you get is exactly the same that we found for the D operator here. Okay, so this factor of P is what distinguishes double versus single trace versions of TTbar. And you can do something similar for the A operator, and you can compute other OPEs with other additional currents, and you find the same story. So all of these hints lead us to conclude that these D and A operators are single trace versions of the TTbar operator or of the JTbar operator. Okay. So now you can imagine deforming the theory by these operators. And in this case, what's particularly interesting is that you end up with a deformation that looks to come purely from the worldsheet, and from the worldsheet, and turns out to be a so-called current-current deformation. So for the D operator, you find only these two currents. This one was from SL to our left, and this one comes from SL to our right. And similarly, for the A operator, you find one from the U1 factor of D4 and another one from SL to our right. Okay, so these current deformations were a long time ago found to be exactly marginal. So they're going to give us new backgrounds, new consistent backgrounds of string theory. And indeed, if you deform the worldsheet action by the single trace TTbar version of this deformation, you obtain a linear dilaton background in the bulk. And similarly, if you do this for JTbar, what you obtain is a warped AdS background. Now, both of these backgrounds have been conjectured to be dual to the Ramond vacuum in single trace TTbar and JTbar, respectively. So again, we can think of this as toy models of holography, where you start with a duality that you know, and you deform it on both sides, and you get both a deformed CFT on one side and a deformed bulk spacetime in the other side. Unfortunately, this approach that I have just described, it's only applicable to the massless BTC background for two reasons, or Poincare AdS. And the reason is that the form of these D and A operators are only known in these cases. Another reason is that when you try to solve for the TTbar and JTbar flow, you need to find these operators along the flow. So as you flow, as you deform the theory, you need to find the operators along the flow. And in these cases above, we only found them at the origin in some sense. So it's not clear to me how one defines these operators along the flow. And so what we would like to do is to find a more general prescription that would allow us to construct more general backgrounds, not just these backgrounds that are dual to the Ramond vacuum, but backgrounds that include black holes and the ground state, which would also allow us to give some non-perturbative tests for these correspondence. So in these cases, the tests come from the perturbative worldsheet spectrum. Okay, so the way we're going to do this is by using TsT transformations. So the main observation that will allow us to generalize the results above is that there is a one-to-one correspondence between the currents of the worldsheet and the dual CFT. So this current of the worldsheet that shows up in the marginal deformation, it generates translations along a coordinate x, a target space coordinate x, which is the same action that the stress tensor has on the dual CFT. And similarly, for this J0 minus bar current, it generates translations along a target space coordinate x bar, which is the same action of T bar on the dual CFT. And similarly, this current here generates translations along the internal manifold, and in the dual CFT, it generates an internal symmetry transformation.
So here, what you don't know is like this explicit expression between those currents, like what you Kutasov and what did Cyberg had before, like an integral. Yeah. That is what you don't have here.
Yeah, these ones here we don't have. Right. Indeed, these ones here we don't have, and yeah, so indeed, so that's one reason, and the other reason is that this TTbar deformation is defined in the following way. So let me just write. For example, the single trace would be defined this way, TTbar, and the currents that appear on the right-hand side are the deformed currents. Okay, so these are operators that are defined in the deformed theory. So it's not clear to me how to define these DNA operators already in the deformed theory. It's sort of a complicated process. And what turns out to happen for the Ramond vacuum is that this equation, so this differential equation simplifies and simply becomes delta S equals mu Ti Tbar I. This is a simplification that happens in this massless BTC or Poincare AdS3, which is what allows us to integrate it easily, right? So when we deform the action in this way, this is a full deformation. We don't have to integrate the flow. It just simplifies a lot. Yeah, thanks for the question. Right, so we're going to circumvent this step of finding what D and A are by using TSD transformations. So there were two main observations. One was this one-to-one correspondence between the worldsheet currents and the currents on the CFT. The other one is that the Noether currents that would generate shifts of the target space coordinates on the worldsheet not always coincide with the Carl-Wessonino-Witten currents. This happens for the Poincare AdS3 and the massless BTC black hole, but more generally, so this Noether current here, the Noether current agrees with the Carl-Wessonino-Witten current up to a so-called topological contribution. This term is topological in the sense that it's conserved of shell. And it's very important because depending on the boundary conditions of the string, this will give you contribution. So if you have a string that winds around the spatial circle and you integrate theta, this will give you the amount of winding of the string. Okay, so what this means is that the previous prescription of just having current deformation, chiral current times anti-chiral current is not going to work. And motivated by the definition of the irrelevant deformations of 2D CFTs, here on the left-hand side, what we have proposed is that on the worldsheet, they take the same form, except that now on the right-hand side, we have these Noether currents from the worldsheet, and this deformation parameter is now dimensionless, okay? Now, we can write this differential equation in a simple way by introducing the following variables. So we write the deformed worldsheet action in this way, where this background field M is the sum of the metric and the B field. And then the differential equation simplifies, or rather can be written in this way, where this gamma is an antisymmetric matrix, and this gamma is here basically because of the wedge that we have in the definition of the deformation. So this wedge here introduces an antisymmetrization that's captured by this gamma, this matrix. And the solution to this differential equation here, it's easy to find, and it's given here, where M hat is the undeformed background. So it's your boundary condition. And this turns out to be nothing but a TSD transformation written in a nice way, which consists of T-duality along one coordinate, shift along another coordinate, and then T-duality along the original coordinate to get us back to the original theory. So what we have proposed is that a single trace, the formation of the 2D CFT, is dual to TSD transformation in the bulk. So we have these relationships. So this is an irrelevant deformation. This one is marginal, at least to leading order in alpha prime. And this is equivalent to TSD. Now, the kind of irrelevant deformation that you get depends on the choice of the TSD coordinates. So in this talk, what I will do is I will consider a sequence of 3 TSD transformations where the TSD coordinates are taken from the Lightcone coordinates of AdS3 in order to get the TTbar deformation. We will take another coordinate from AdS3 and one from T4 to get the TJbar deformation. And similarly, a different coordinate of AdS3 and another one of T4 to get the JTbar deformation. So because we have taken the same coordinate of T4, this Y coordinate here, the J and J bar currents in the dual theory in this JTbar and TJbar deformation are going to be the same current in the dual QFT. Which is to say that we could have chosen different currents. We could have chosen a TSD transformation where we take a different coordinate of T4 or a different coordinate of S3, And all that you will do is you will get backgrounds that are way more complicated, but conceptually are the same as the ones that I'm going to consider. So, but they were considered before in these papers. Okay, so do you have any questions?
Like taking two coordinates in the compact space is like, that would be then a JTbar because you're not deforming the.
Exactly, that would be just like a marginal JJbar deformation on the worldsheet. Oh, sorry, on the dual theory. Yeah. Okay, so yeah, so this will be the main idea that we're going to exploit now. So my starting point will be a 4-parameter family of charged black holes. So I've written this in 10 dimensions because I need to do the TsT transformation in 10 dimensions, but I have written it in a 3-dimensional language because all of the calculations simplify in 3 dimensions. So the things worth stressing here is that the 3D metric is just the BTC black hole where TU and TV are proportional to the temperatures of the black hole. In addition, if you set TU equals to TV equals to 0, you go back to the previous massless BTC case. And if you do the analytic continuation where TU squared equals TV squared equals minus 1/4, you can get the ground state geometry. This background features an energy. So there's a left moving energy, there's a right moving energy with the conventions that the total energy is the left plus the right, and the angular momentum is the left minus the right, as well as 2 U1 charges that are given here. And that's the reason why we have turned on these 2 gauge fields. So after we perform TsT on this background, we are going to get a 7-parameter solution to the supergravity equations of motion that we claim is the most general charged black hole that you can get in this single trace TTbar plus JTbar plus TJbar, the form CFTs. And in this case, so TU, TV, alpha U, alpha B will be phase space parameters. So they will describe different solutions in this theory. As you can see, they parameterize the energies and the UN charges. Whereas these parameters correspond to the deformation parameters. So they're going to be fixed. Right, so because this is a 7-parameter solution, which I will show you later is quite complicated. So it's easier to first consider a few simple cases. So let me start with the TTbar case. So in this case, we set these deformation parameters to 0, and I also turn off the UN charges. So when you see these alphas, you think immediately of the UN charges, so I'm turning them off. So in this case, the 3D background that you get after performing the TsT transformation is this one. And in particular, you see that as R goes to infinity, this part of the metric can be written in this way. And it's no longer asymptotically AdS. So you've changed the asymptotics. In fact, this background turns out to be asymptotically flat. So its curvature vanishes at infinity. It features a horizon at this value of the radial coordinate, which is the same, that the location of the horizon has not changed after performing the TsT transformation. And the physical temperatures of the black hole have been changed as well. Now, did you lose my iPad?
Yeah.
Yeah, sorry about that.
The iPad is still a host, right? Or is it not?
It is still, but I have the bad habit of pressing the button on the right-hand side, and then it turns on. Okay, can you see it again?
Yeah.
Okay, sorry about that. Okay, so right, so there are these deform temperatures, and I have written these deform temperatures for the following reason. If you want to keep the dilaton real, you find that these deform temperatures must satisfy the following bound. And the reason why this is interesting is because if you take a TTbar deformed CFT and you didn't know anything about this background, then you would find the same bound. So a TTbar deformed CFT satisfies the same bound on the deformed temperatures. which is a consequence of the Hagedorn growth of states, which we will see more about later on. Interestingly, these backgrounds that we have constructed are not totally new. So when TU equals TD, meaning when the angular momentum is 0, they belong to a space of asymptotically flat black holes that were studied by Horn and Horowitz a long time ago, if we choose the deformation parameter to be 1. The Horn-Horowitz solutions are obtained from a gauge-Wessumino-Witten model, and it turns out that something similar can be done for the more general case that we have, except that you have to perform some additional changes of coordinates and some shifts of the B field and a shift of the dilatant. But they're locally, at least the metric is the same. It's locally the same. Now, when we stare at these solutions for some time, you will find that the vacuum, the ground state solution is real, provided that this parameter is less than 1, and that the solution develops CTCs, closed time-like curves, and curvature singularities at some value of the radial coordinate, whenever this lambda naught parameter is negative. So what I have plotted here is the Ricci curvature, the Ricci scalar in the Einstein frame. And you see that deep in the IR, so near R equals to 0, the curvature is negative, as we expect for the AdS3 background we started with, whereas deep in the UV, the curvature goes to 0 because it just becomes asymptotically flat for these backgrounds. And at some point, at some value of the radial coordinate, shown here in red, you start finding CTCs. And for TTbar, this location of the CTCs and the singularity, they agree with each other. Now, why do I mention these pathologies? Because from this from looking at these pathologies, we learn that the backgrounds are going to be healthy, provided that this constraint is satisfied on the deformation parameter. And interestingly, so the pathologies that I just have described are consistent with the existence of complex energies in the spectrum of TTbar deformed CFTs. So I have written here the form energy of TTbar again. And what you will notice is that for the ground state, where the energy is minus C/24, the deformed energy becomes complex unless the deformation parameter satisfies this condition, okay? And similarly, if you go to very high energies, the spectrum will also become complex whenever the deformation parameter is less than 0. So we see that this solution, just by studying geometrical aspects of this solution, we find that they have a lot to do with this TTbar deformation. Now, in the double trace version of holography, these complex energy states that appear when you take mu to be less than 0, they are avoided by putting a cutoff that scales in the following way. And in the single trace version, this cutoff has not been, no one has tried to find a cutoff version of holography yet, but the natural location of this cutoff would be the location of the CTCs and singularities. So this red line here, and you see that in this case, the deformation parameter also scales as, the location of the cutoff would also scale in this way, as in the double trace version of holography. So it would be interesting to see if this also works in the single trace case. Okay, so now let me describe another simple case, which is the neutral JTbar case, where we turn off these deformation parameters, and it's neutral because we also turn off the U1 charges. In this case, the deformed background is given in this way. And again, we can expand near R equals infinity, where we get the following metric. So if you try to deduce what the boundary metric is for this spacetime, you would find that it's null. This is characteristic of warped AdS backgrounds. Again, this is not a locally AdS background anymore, even though it does have a constant negative curvature. And the other thing that you notice is that because of this minus sign here and here, this background features CTCs for all values of the deformation parameter. This sounds puzzling, but now if you look at the spectrum of JTbar deformed CFTs, which is also given by this squared structure, you see that the deformation parameter enters as mu squared, and there's a minus sign here. So the spectrum of JTbar deformed CFTs features complex energy states at high energies. Okay, so this is another coincidence between this background and JTbar deformed CFTs. And in order to remove this negative sign, and in order to remove the CTCs from the bulk, we should also turn on the TTbar deformation. So this leads us to the most general case, which is quite complicated. The thing that I want to stress here is that this background, like the one we started with, features 4 charges. There's a left moving energy, a right moving energy, and 2 U1 charges. And these U1 charges do not vanish as long as these parameters are not 0. So again, having these alpha parameters are necessary to describe the most general space of solutions. And these were parameters that were missed in previous papers. Okay, so in the general case, we can perform a similar analysis, and we find that in this case, real solutions that are free of CTCs and curvature singularities require the following bound on the deformation parameters, which is a generalization of the one we found for the TTbar case. It's worth noting that this condition is universal, so it does not depend on the phase space parameters. It doesn't depend on the solution, so it's really telling us something about the dual theory. And indeed, you find that in TTbar plus JTbar plus TJbar deformed CFTs, the spectrum becomes complex at either high energies or for the ground state if either one of these conditions is violated. However, unlike the TTbar case, we now have a more interesting phase diagram of the possible choices of deformation parameters that I've plotted here. So again, here I'm plotting the Ricci scalar in the Einstein frame. So for the healthy case, again, you see deep in the IR, the curvature is negative, as we expect for the pure AdS3 background, and becomes flat at infinity. Then we can consider different choices of deformation parameters. For example, in this case, we have CTCs, but no curvature singularities. For this choice of parameters, we have CTCs and 1 singularity, and the location of the CTCs and the singularity differ by terms that are proportional to alpha u and alpha v. So for the TTbar case where we turn out these parameters, these two coincided. That's the reason why the two coincided. And in the worst case scenario, you can have CTCs and 2 singularities if you make this choice. I don't know how one would see the singularities in the TTbar CFT. We clearly have a connection between CTCs and the emergence of complex energy states. But it would be interesting to see. We can also figure out what do these singularities correspond from the TTbar point of view. But this is something we don't know yet. Okay, so everything that I have discussed so far are just hints that we indeed, these backgrounds and TSD transformations indeed have something to do with TTbar and JTbar deformed CFTs. So what I'm going to do now is provide 2 evidences, 2 pieces of evidence for the correspondence. One will be perturbative, the other one will be non-perturbative. The perturbative one comes from looking at the spectrum of strings winding on this background. And so the way we're going to derive the spectrum is by spectral flow transformation. So let me say a few words about spectral flow. So spectral flow plays an important role in string theory. And at the classical level, it helps us generate winding string solutions. So these images are taken from a paper by Mateseno-Guri from 2000. So if you imagine taking the worldsheet equations of motion and you find a timeline geodesic, this is a solution to the equations of motion, and performing the following shift of coordinates, you will generate a new solution to the equations of motion that corresponds to a winding short string. So this is a string that just contracts and expands in the interior of AdS, and it reaches a maximum size. And here W corresponds to the winding of the string along the spatial circle. Similarly, you can start with a space like geodesic here, perform the same shift of coordinates, and now you will generate a long string solution, which is a solution that comes from infinity, goes to 0, and then expands again. And again, this W is the winding of the string. Now, the shift of, yeah, was there a question?
Yeah, Z and Z bar are worldsheet coordinates, is that right?
Yes, indeed, yes. Z and Z bar are worldsheet coordinates, U and V are the target space coordinates. Yeah, thank you. Right, so yes, the shift of coordinates corresponds to an automorphism of the Saltor algebra. This is just a spectral flow transformation, and it induces a shift on the stress tensor. And you can see the shift by recalling that the stress tensor is given by the Suawara construction like this. And one of these currents shifts linearly under spectral flow, which explains the presence of this linear term here. Now, if you impose the Virasoro constraints, meaning if you impose the mass shell condition, then you will find the following relationship between energies where the winding is turned to be an arbitrary value, and the energies when the winding is 1. And this formula here is very interesting because this is nothing but the conformal weight of a twisted state in a symmetric orbital. Okay, so this formula plays an important role in this conjecture that the long string sector of string theory in AdS3 is dual to a symmetric orbital. Okay. So for the backgrounds we have constructed, we're going to use a similar approach. And the reason we can do this is because, as is well known, the equations of motion and Virasoro constraints on TsT-transformed backgrounds can be related to the undeformed quantities by a non-local change of coordinates that takes this form. Here, so maybe let me write the worldsheet current can be written in the following way. And you see that, so some pieces of the worldsheet current appear here. And this change of coordinates induces twisted boundary conditions on the x-hatted coordinates, so that as you go around 2 pi, you pick up, in addition to some winding that you may want to have, you pick up these terms, where P is the momenta associated to the worldsheet current. Was there a question?
No, I don't think so.
No, okay. Right, and you see that this moment appears here because in the non-local change of coordinates that are associated to a TsT transformation, the Noether currents are featured here, are secretly featured here. So provided that certain conditions hold, and these conditions do hold for the AdS3 cross S3 cross T4 pattern we're interested in, you can implement these boundary conditions by a spectral flow transformation that is induced by the following change of coordinates. So for AdS3, we have this change of coordinates. So here, for example, for TTbar, this would be U going to U, and this would be V going to V, which are generalizations of what we find for just pure AdS3. And for the T4, we impose this shift of coordinates. And the reason why they differ is it's a bit technical, and I can say more about it later on if you're curious. Okay, so now you play the same game, you perform the shift of coordinates. This is equivalent to a spectral flow transformation. It shifts the zero modes of the stress energy tensor in this way. And if you impose the Virasoro constraints before and after the TsT transformations, you find the following relationship between the deformed and undeformed charges. So here, the left moving charge is identified with Pu. The right moving charge is Pb with a minus that comes from our conventions, and Py, which is the momentum along y, is written in terms of a left and right moving U1 charge. The thing to note here is that if you now try to solve for the deformed spectrum, you're going to get the characteristic square root of TTbar and JTbar deformations. And this is a generic feature of TsT, because if you look at the effect of the TsT transformation and the shift of the stress tensor, you find that all of these terms are either linear or quadratic on the energies. And for this reason, you're going to get square roots for the expressions for the deformed spectrum. It's not obvious from this expression, but after you try to solve it, you find that indeed the spectrum will become complex at high energies if this condition is satisfied, unless this condition is satisfied, which is also what we found from the bulk by trying to remove closed timeline curves. So this is the worldsheet spectrum, and now we are going to give it an interpretation in terms of the deform theory. So as I mentioned before, what's magical about a single trace deformation is that it takes a symmetric product and it gives you another symmetric product. And a symmetric product features both twisted and untwisted states. So as before the deformation, it's natural to identify the winding of the string with the twist of a single particle state in the symmetric orbital. This would mean that when the winding equals 1, we have an untwisted state, whereas when the winding is greater than 1, we would have a twisted state. What this means is that the energies of the states with winding 1 should match the spectrum of the seed TTbar plus JTbar plus TJbar deformed CFT. And this turns out to be the case. So if you look at the formulas that I have written here, and you set the winding to 1, you recover the spectrum of these deformed theories. So for example, the simplest state in the untwisted sector of the dual CFT is the ground state, which I've written here. And this ground state matches the energy that we derive from the worldsheet, so the expression here. But it also matches the energy that we can compute from supergravity. So some time ago, I showed you that this TsT-transformed background was characterized by 4 charges. And if you do the analytic continuation that takes you from those solutions to the ground state, you see that the same energy pops up. So we can see explicitly that this is indeed true. The states with winding 1 correspond to untwisted states in the deformed theory, whereas the states with winding greater than 1, we have not checked. This is an expectation. And the reason we have this expectation comes from considering simpler cases where we can show that this is indeed the case. So how much time do I have, by the way?
10 minutes.
10 minutes, okay. Right, so this is an expectation that we have for this most general class of deformations, but we can show that it's indeed met for some simpler cases. And the simpler case is the TTbar deformation. So what I will show now is how, what the spectrum is of a single trace TTbar deformed CFT, and that it matches the worldsheet spectrum. Okay, so to derive this spectrum, we first need to identify the contributions to the partition function coming from the untwisted sector. And it turns out that this contribution is universal. It's valid for any symmetric orbifold of any kind of theory you would have, but this confused us a bit at the beginning, so I will just provide some intuition for it. So let me first consider the case where p equals 3. So remember, the symmetric orbifold has a factor of p here. It counts the number of copies you have. So the state in the untwisted sector are of this form, meaning that phi is, we symmetrize 3 fields coming from different copies of the symmetric orbifold. But within this structure, there are different classes of states we can distinguish. There are states of this form where all of the states are the same in each copy. And in fact, in this case, we don't need to symmetrize because such states are already symmetric under the action of the symmetric group. We have states of this form where two of the states are symmetric, and we have states of this form where none of the states are the same. And the reason we make this split is because then we can count their contributions to the partition function. So for the states where all of the states are the same, their conformal weight is given by 3 times the conformal weight of the field feature here. And as a result, the partition function is just given in this way, or the contribution to the partition function is given in this way. For these kind of states, the conformal weight is 2 times the conformal weight of some state, because there were 2 states that were the same, plus some additional conformal weight, with the constraint that H1 is not equal to H2. Okay, so this factor of 2 here explains the presence of the 2 tau here. And this constraint means that we have to remove some extra piece. And a similar logic leads you to the contribution from the most generic state to be this one here. Now, when you add up all of these terms, you end up with the contribution of the untwisted sector to the partition function, which looks like this. And this is nothing but the cycle index of S3. If we identify this partition function with the trivial conjugacy class of S3, so the identity, if we identify this with the Z2 conjugacy class of S3, and this one with the Z3 conjugacy class of S3. And in this case, these coefficients here are just the size of each conjugacy class. In other words, that's what it means for this to be the cycle index. More generally, for arbitrary P, the partition function is given in this way, where here we're summing over all conjugacy classes, and this term here counts the number of terms in each conjugacy class. So this is a well-known formula that was found long ago. It's a well-known formula. It works for any symmetric orbifold of anything. It doesn't have to be a CFT. It's just a counting problem. What is different for, say, a TTbar deformed CFT versus a CFT comes from the twisted sector. So the spectrum of twisted states in a symmetric orbifold can be deduced by imposing modular invariance of the partition function. Now, it turns out that TTbar deformed CFTs are modular invariant in the following sense. So we have the usual transformation of the modular parameter of the torus, but in addition, we have the scaling of the deformation parameter. And because in the TTbar deformed CFT, we no longer have a local Virasoro symmetry, the partition function is defined in terms of the energies instead of in terms of the conformal weights. So it's natural to assume that the partition function of the full symmetric orbifold that we've denoted by ZP is also modular invariant. There's a star here because there's a subtlety in this statement that I can also tell you about later if I have time. And it will transform in the following way, which is clearly not the same. And the way to make these contributions, these terms, invariant is by adding all of the modular images under the modular group. And this can be easily accomplished by the following replacement. So we take each of the Zn terms in the partition function and we replace it by these functions, where T here is a generalization of the Hecke operator that is appropriate for a TTbar deformed partition function. So the usual Hecke operator is defined in this way, but because TTbar deformed CFTs have this additional deformation parameter, and because of the transformation and because of the modular transformation properties, we also need to include this additional term in the definition of the Hecke operator. So if you put all of these ingredients together, you find that the motor invariant partition function of a single trace TTbar deformed CFT can be written in closed form like this. And again, this is the same formula you find for a CFT, except that the Hecke operator is defined in a different way, okay? And again, this comes just from the different motor properties of these theories. Okay, so once we know the full partition function, we can read the spectrum of twisted states. These are the states, the additional states that we have added to make the partition function motor invariant. And after a short calculation, you find that the contribution of the twisted states is given in this way. So what this means is that whenever you have a state with energies E left and E right in the seed theory, you're going to get another state coming from the twisted sector that is given in this way. And if you look at these formulas, you see that they are also the same formulas that you find in a CFT, except we have to do an additional rescaling of the deformation parameter, which again comes from the interesting motor transformation properties of the theory. So now if I use the expressions for the undeformed energies that I know from the TTbar literature, just these square roots, I can find the expression for the twisted states in the deformed and undeformed, the relationship between the deformed and undeformed twisted states, which are given like this. And these expressions match exactly the spectrum you get from the worldsheet if you identify the winding with the twist of the state. Okay, so I expect a similar approach to work for the more general TTbar, JTbar, and TJbar deformed CFTs we've been considering. And the reason we haven't done this yet is because the motor transformation properties of these partition functions are not known yet. And in fact, it's not clear if one can even write them in closed form. So you see here, the partition function transforms nicely. It's a closed form expression. What one can do is try to expand mu naught perturbatively and try to deduce the motor transformation properties in this way, and then resum the whole answer, and it resums into this. But in these cases, it's not obvious if the resummation is possible. Okay, but nevertheless, I think, I think that the spectrum of the worldsheet should correspond to the twisted states in the deformed CFT. Okay, so this is a perturbative check. We can also have a non-perturbative check. I think I'm running out of time, so I will just tell you quickly what the answer is. So for the non-perturbative check, we take this family of TsT-transformed backgrounds that I showed you before, and we compute the entropy. So in the supergravity approximation, we just have gravity plus matter field, so we know how to compute the entropy. It's given by the area of the horizon, and we obtain the following formula. What's interesting to note here is that this combination here turns out to be the deformed U1 charge, so that this expression roughly, it's roughly similar to what you expect from Cardy's formula, which in the undeformed theory can be written in this way. Another thing to note is that if you make the energies large, this entropy scales linearly with the energies, because you see there's an energy here and an energy here, which is the characteristic behavior of these theories. It's this Hagedorn growth. And we can also check that the first law works, where these chemical potentials are proportional to the alpha U and alpha B parameters I mentioned before, so that we have consistency checks that we have gotten the right expressions. And you can similarly derive this from the worldsheet, from the dual side. And the derivation is a bit complicated, so I will just skip it and give you the final answer. So if you take the symmetric orbital and try to compute the density of high energy states, you end up with this formula. And the two things to note about this formula is, first, it matches exactly what we find from the bulk. So This indicates that these black holes that we find in the bulk should be interpreted as thermal states in these deformed CFTs at the boundary. Another thing to note is the factor of P that enters here and here, which distinguishes the entropy from the single and double trace cases. So in the double trace case, the entropy can be obtained if you set P equals to 1. But in the single trace case, there is this, there are these additional factors. So we can indeed distinguish which kind of theory we have at the boundary. Okay, so there are some additional ways we can try to derive this entropy that I will not mention at the moment, that rely on exploiting the motor invariance of the theory in a different way. Okay, so what I have provided evidence that these TsT transformations of AdS3 backgrounds with NS and S flux yield spacetimes that are dual to states in single trace deformed CFTs. And something that would be interesting to do in the future is to, and something that we're thinking about is to consider the contribution of Fermions and extend the analysis to finite K. So our analysis has been done in the limit that T was much greater than 1 and K was much greater than 1. And in fact, in the AdS3 literature, in the literature of string theory and AdS3 with NS and S flux, the duality with asymmetric orbital at the boundary has been proven for the case K equals 1. And so it would be interesting to try to do the same here. In that case, we don't have a supergravity approximation, but that should not be necessary. We can just do the analysis from the worldsheet. Similarly, something that I think it's interesting to think about is whether we can exploit TsT transformations further to provide more evidence for the correspondence. So for example, we use TsT to derive the spectrum in a simple way. Whether there are other ways in which just TsT can tell us about single trace deformed theories. Similarly, I think it would be interesting to make sense of a cutoff when the coupling is negative in the single trace version of holography. The emergence of the CTCs sort of tell you exactly where the cutoff should be imposed. And what would be interesting would be if this can be generated dynamically within string theory. And finally, these warped AdS spacetimes that I mentioned that show up in the context of the JTbar deformation are featuring other holographic correspondences, so to warp CFTs, and as we have seen, to JTbar deformed CFTs. And it would be interesting to see if these theories are related. At least in the context that we have worked in here, we see that these are indeed JTbar deformed CFTs, but in different contexts, they belong to the space of warp CFTs. And well, yeah, it would be interesting to see if these two theories are somehow related. Okay, that's all I wanted to share. Thank you for your attention.